In this series of videos, we're going to learn about a type of compound called a pH buffer, which is actually not a single compound, but a solution that contains both a weak acid and the conjugate base of that weak acid in close, if not identical, concentration. For example, if we have a 1.0 mole per liter solution of acetic acid and then add 1.0 moles per liter of acetate to that solution, we have just made a buffer solution because we have an acid, its conjugate base, and they exist in equal concentration, although equal concentration is not necessary for reasons that we'll see. We can observe the buffer's effects on pH change by taking a look at this graph, which represents pH on the y-axis contrasted with volume of base added to this solution on the x-axis here. Obviously, as we increase the amount of base that we add, the pH is going to increase with it as well, which is exactly what we see. But if we look in the middle of the graph right here, we can find a specific region of the graph called a buffering region, in which the pH remains not exactly constant, but very, very close to unchanging. So from this, we can see that the presence of a buffer solution has a stabilizing effect on the pH and prevents any large pH change until the buffer is pushed too far in either direction. What exactly does this mean? Well, let's take a look at the mechanism of the buffer at the atomic level. So because we have the weak acid, acetic acid, if we were to add a base, again, which we can represent with hydroxide here, the base that we add would remove the ionizable hydrogen from the acid form of our buffer and give us water, again, thus showing that the buffer helped to neutralize the base that we added here. If we do the same with acid, because we have acetate, which is the conjugate base, it can use one of its lone pairs to form a bond with the extra hydrogen on hydronium, breaking it, and therefore giving us water again, thus neutralizing any acid that we have. So a buffer solution keeps the pH of a solution stable by neutralizing any acid or any base that is added to the solution, which is why we need both a weak acid and its conjugate base so that we can neutralize either acid or base that is added to the solution. We can observe the effects of a buffer mathematically as well. So if we consider the hypothetical buffer solution from above that contains 1.0 moles per liter of acetic acid and acetate, we can write out the Ka expression for the ionization of acetic acid. It's exactly the same as it usually is, where we have the concentration of our conjugate base times the concentration of H3O plus divided by the concentration of the acid form. Now, this is important. The fact that we have an equal concentration of acid and conjugate base, meaning that the ratio of acid to conjugate base is equal to 1, meaning that we can cancel each of these, and our Ka is simply equal to the concentration of H3O plus. If this looks familiar, that's because we just described the transition point again. So transition points occur not just with pH indicators, as we've seen, but occur with any mixture of weak acid or base and its conjugate. And we can see that the transition point occurs right in the middle of this graph here, right at this point, often what we call the half equivalence point. Now, this has interesting ramifications when we actually go and look at how adding acid or base is going to influence the pH, because we know that at the transition point, the pH of our solution is simply equal to the negative log of the Ka of the weak acid that we have in our buffer solution. So we can use this as our starting point and compare what the effect of adding a small amount of acid or a small amount of base to our buffer solution is. Now, if we want to add HCl to our buffer solution, because HCl is a strong acid, it's going to ionize 100% with water in order to form the same number of moles of H3O+. So adding HCl is effectively the same as adding H3O+, and because H3O+ is an acid, we know that this is going to react with acetate because this is the conjugate base. So what this means is that when we add 0.1 moles of hydronium or of acid to our solution, this is going to be neutralized by our conjugate base, which then turns into water, which, because the acid has been neutralized, and the acid form of our buffer solution, which means that if we need 0.1 moles of acetate to neutralize this, we are going to produce 0.1 moles of our acid when the conjugate base takes the extra hydrogen from hydronium. So our change that results from here is that the acid gets neutralized, our conjugate base decreases by the same amount because we need the same number of moles to neutralize this amount of acid, and the base that is neutralized gets converted into the conjugate acid, which means that we now know what our new equilibrium concentrations of each of these are going to be. Well, with one exception, because the equilibrium is going to shift, so we don't know how much hydronium we're going to have, but we do know that the concentrations of our acid and of our conjugate base are going to compensate based on the amount of extra hydronium that they neutralized, and we can calculate the pH of the resulting solution relatively easily. So if we assume that our solution is 1 liter, we know that our concentration of the acid is 1.1 moles per liter, and our concentration of the conjugate base is 0.9 moles per liter. So all we need to do is put those into our Ka expression and solve for our concentration of hydronium and take the negative log of the number that we find. If you put these numbers into your calculator, you'll find, remembering that the Ka of acetic acid is 1.8 times 10 to the negative 5. If we put all of these into our calculator and solve for the concentration of hydronium, you should find that this concentration comes to exactly 2.2 times 10 to the negative 5, which again is a little bit greater than the concentration of hydronium that would exist at the transition point, but is not significantly different. Then if we take the log of our concentration of hydronium in order to find the pH, you should find that this number comes to approximately 4.65. Now, if we want to compare this with the pH at the transition point, all we need to do is take the negative log of Ka, and that would be equal to our pH. So if we do that, our pH at the transition point, before we added in the extra volume of acid, comes to approximately 4.74. So you can see that the pH has dropped from 4.74 to 4.65, which means that it is a little bit more acidic, but this is not a really significant change, especially if we compare this to adding the same amount of hydronium directly to 1 liter of water. So in this case, if we take 0.1 moles and divide by 1 liter of water, our concentration of H3O plus is 0.1 moles per liter. And if we take the negative log of this number, of our concentration of hydronium, we would find that our pH is 1. Now, pure water has a pH of 7, and simply by adding a small amount of acid, we've dropped the pH by 6 orders of magnitude, whereas we didn't even drop it by 0.1 orders of magnitude with a buffer solution. So this is how effective buffer solutions can be in terms of resisting pH change. We can do a similar calculation to show the effect of adding a small amount of base to our solution. So remember that adding NaOH, we don't really care about the Na plus because it's not going to do anything and it's going to act as a spectator ion. So what we're really interested in is the OH minus that we're going to add. And because OH minus is a base, we expect that this would react with the conjugate acid in our buffer solution. So in the same way that we saw the equilibrium move around when we added acid, if we add in base, we know that you need the same amount of acid in order to react and neutralize this base. So we would expect that our acid number of moles would decrease by the same amount as the base that we added in order to neutralize it. And because the acid loses its H plus when the hydroxide reacts with it in order to make water, we would expect that this acid gets converted into the conjugate base, and so we have very similar numbers as the previous situation, only now we have more base than acid. And if we want to actually see what the effect of this is going to be on pH, we can put this into our Ka expression. So here, because we have more base than we do acid, 1.1 would go here, times the concentration of H3O plus that we would want to find, times or divided by 0.9, which is the new concentration of acid that we have. And we remember that our Ka value of acetic acid is 1.8 times 10 to the negative 5. After rearranging this, if you solve for the concentration of H3O plus, you should find that this comes to approximately 1.47 times 10 to the negative 5. So again, if we compare that to the original amount of hydronium that we had in our transition point, we can see that there is a little bit of a decrease, but not a significant amount. And again, we can see that the pH has not significantly changed either by taking the negative log of this concentration of hydronium. And if you put this into your calculator, you should find that our pH comes to approximately 4.83. So if we compare that to a pH of 4.74 of our buffer at the transition point, we see that the pH has increased a little bit, but very insignificantly compared to how adding 0.1 moles of hydroxide directly to water would do so. So in this video, you should have seen whether we look at the mechanism of how a buffer solution works, and when we do some fairly rudimentary pH calculations, it should be obvious the degree of which a buffer solution can stabilize pH. And in the follow-up to this video, we'll take a look at some of the more complex calculations that are involved with buffer solutions.